Good morning to everyone. This is the DDay 2018. Welcome to the student and the colleagues of the doctorate, ICT doctorate. We will have some presentation in live and other in video, because some of our graduated students are already working outside, and so please, the first doctor is Lorenzo Baraldi, who will present his thesis work.
So good morning to everyone, and my name is Lorenzo Baraldi, and the title of my research activity is Multimedia Technologies for Video Analysis, Retrieval and Description, and my supervisor is Professor Rita Cucchiara. So the motivation behind this work is that the growth of the usage of videos online demands for effective multimedia technologies for browsing, retrieval and indexing. And we tackle this research activity under three main research directions during the 3 years period. The first one is temporal video segmentation, then image and video captioning, and finally temporal video alignment and retrieval. And this last part of the activity has been carried out during an internship at Facebook, and I also took part to 2 national projects, namely Città Educante and Cult Media. So, starting from temporal video segmentation, the motivation behind this is that browsing video content is not easy, and so we found that professional edited video have a well-defined structure that we can leverage for enhancing browsing and retrieval. And this structure is that the one that has frames at the bottom level, then shots, and then scenes. So this is actually a multimodal problem, so we need to take into account different modalities and also some high-level semantics to be able to tackle this problem. So we cannot leverage visual features only. And it is also a subjective problem, and so if you ask different annotators to annotate the same video, you will probably get different annotations, and so you need a way to tackle this, and for this we actually built an algorithm which is able to find the best, the ideal segmentation given a set of human annotations. So during the 3 years PhD, we actually built a set of different multimodal architecture for scene detection, and this is the last and the best performing one. So as you can see, it contains a variety of different multimodal features, visual appearance, audio, time, and semantic features extracted from the transcript. And it is based on a learning approach in which we are building a semantic embedding space, which is trained using a triplet loss. And once this embedding space is trained, we then perform a temporal clustering step by minimizing the variance inside each scene. So basically, the objective function that we are optimizing is the minimization of the sum of the variances inside each scene, plus a penalty term which is needed to avoid over-segmentation. And we do that without knowing the number of scenes in advance. These are some qualitative on the left and quantitative on the right results. So on the left, in the first bar, you see the ground truth in the first blue bar. Then the green bar is the results of our methods, and the remaining orange lines are the results of other methods which were found in literature. And you have more or less the same in the table on the right. So as you can see, we were able to get some segmentation which were a bit closer to the ground truth with respect to the other methods. And a nice application that we did on scene detection was to build a retrieval algorithm on top of scene detection. So it is a retrieval algorithm which works at the scene level and which is driven by semantic concepts which are found in the transcript. And we also coupled this with a thumbnail selection approach, which we built an aesthetic ranking model using CNN features extracted at different levels of convolutional neural networks plus using a centered fixation prior to give more importance to the center of the image rather than the periphery. And if you look at the two qualitative results that I put at the bottom of these slides, you will see that thumbnails in which we have a clearly visible object in the middle on the left are preferred with respect to thumbnails with poor aesthetic quality or without a clearly visible object in the middle. A nice thing about this also is that we built an interactive demo which is called NeuraStory. NeuraStory is an interactive multimedia system for video indexing and reuse. And in NeuraStory, basically each video that is uploaded is decomposed into its storytelling structure by using the scene detection algorithm that we saw before, and also by coupling this with the retrieval strategy that I just presented you. And this actually is able to enhance browsing and retrieval. And just to give you qualitative idea of this is how video is presented in NeuraStory. So it is presented in a timeline fashion. Each item in the timeline is a scene, and each scene is annotated with its keyframes, the transcripts, and the visual concepts which are found inside the scene itself. So coming instead to the second part of the research activity, image and video captioning. So captioning is the ability to describe visual content, either images or video, in an automatic way. And the motivation behind this is that it actually enables us to build a bridge between vision and language, and therefore it enables us to retrieve visual content with free natural language query. It is still an open problem, and the usual structure for video captioning, instead of having a recurrent neural network on the top to encode the input video, and the second recurrent neural network to generate the target sentence. And here I took three main research directions. The first one is the study of the architecture of the video encoder. The second one is the ability to name characters with their proper names in captions. And the last one is the study of the areas of attention and of eye fixation for image captioning. And for time constraints, I will give you only a glance of the first part, and I will skip the other two. So studying the architecture of the video encoder, we found that the idea of encoding the input video with a single LSTM layer, given that a video has layered structure, so with different shots, different appearances, different actions, may not be the ideal strategy. And so we propose a cell which is capable of identifying discontinuity points and actually modify the layer connectivity through time accordingly. So this, for the first time, is an example of a video encoder which has a connectivity schema which is thought as an activation instead of being an unlearnable hyperparameter which is fixed a priori. And so it is an activation in the sense that it is learnable and it depends on the actual input. So these are some qualitative results on two video captioning datasets in comparison with the state of the art and in comparison with some challenging baselines as well. So as you can see, we were able to get quite an improvement over the state of the art. And finally, these are some qualitative results as well. So here you have a vertical blue line every time that the boundary detector inside the cell is activated, which means that the layer actually detects that there is a change in action or appearance inside the video, and it modifies the connectivity through time of the cell accordingly. So for example, if you look at the middle one, the ground truth shakes his head, and the prediction of our boundary encoder was someone looks at someone who shakes his head, which is fairly correct, and the three boundary activations here actually correspond to appearance change and action change. And if you look at the other two, the first one and the last one, more or less the situation is the same. So the boundary detector actually activates during an action change or an appearance change. And finally, the last part of this presentation is about video alignment and retrieval. And this part, as I was telling at the beginning during the introduction, has been conducted during my internship at Facebook AI Research. And here we built a learnable temporal descriptor for video alignment and video comparison in general. So if you look at most of video descriptor in literature, they actually they usually pull over the time dimension of the video, and therefore they lose any temporality. And instead we took quite a different approach, and so we took inspiration from temporal kernels and from the parametrization in the Fourier domain, and we built a video descriptor in which we have a fixed dimensionality, even though it can take variable length data as input, and in which we can always compute the similarity between two videos, even though we shift temporally one of the two. And this is done by relying only on the video descriptor, so without actually having to store the frame level descriptors. And finally, this is a descriptor which has an high localization and comparison accuracy, even though we actually retain only a few frequencies, thanks to the fact that we take different Fourier transform with multiple periods. And plus the parameters of this layer are actually learnable, so they can be learned through stochastic gradient descent. So just to give you an idea of how this works, in the top part of the slide you have the responses of each of the individual filters which are inside the layer, and each filter is built with a different periodicity. So you see that and they have different periodicity actually, and the filters which have higher periods tend to be less accurate in terms of localization. But if we actually combine all these together, we get a signal which is not periodic and which is actually quite accurate in terms of localization. Here the ground truth localization point was delta equal 1000, and so if you look at the combined response, it's actually quite accurate. And the nice thing about this is that it gives state-of-the-art results not only for video alignment but also for event detection and video copy detection. So the nice thing is that it actually works fairly well even in case of event detection, in which you need higher level semantics and not only video alignment from in the temporal domain. So these are the quantitative results for video alignment on two state-of-the-art datasets for these tasks in comparison with CTE and TMK, which are two of the most challenging approaches in literature. And as you can see, we get quite an improvement in terms of localization accuracy. And here you have more or less the same for the case of video copy and video event detection. And again, there is quite an improvement over the state of the art. And this was actually submitted to CVPR, and this morning I got the news that it has been accepted.
Oh, very good.
So yeah, 5 minutes ago.
Lucky day.
So to conclude, the goal of the PhD was to enable a better understanding of the video content, and we did this by studying the temporal dimension of videos and by trying to bridge together vision and language. So for the first part, we actually study how we can decompose, present, and represent the temporal axis of the video, and we did that by tackling scene detection, in which we studied how we can decompose long videos, and in the case of the learnable temporal match kernel. And for the second part, instead, we did this in the case of the boundary aware video captioning encoder, and I'm also doing this in some ongoing work, so generating the description with proper names, and trying to go from caption to video descriptor and back, what I call cycle captioning, which is something that we are doing in cooperation with the University of Aalto, and also the use of quasi-recurrent architecture for captioning as well. So to conclude, this is the list of my publications, so the list of submitted papers, and the list of journals, and finally the list of conferences. So That concludes my presentation, so thank you.
Thank you. Very good. There are questions from the... You are too clear. Lorenzo, compliments for your work, and if you need some similarity algorithm for the description, we have a very good one. We just have accepted one paper on information system yesterday.
So we'll definitely take a look.
So the next presentation, live presentation, is Du Song.
Good morning to everyone. I'm Song Du, and my supervisor is Professor Sonia Bergamaschi. My research topic is big data integration, and I focus my study on scalable join algorithm. And the outline of my presentation is we start with a brief introduction to data integration and big data, and we continue with two join algorithm I studied, and the conclusion of my PhD studies. Let's start from data integration. Give two or more data sources. Data integration provides a unified view of this data. In this example, we have Momis as data integration system, and the user query Momis system to get the data of underlying sources. And the big data, we study big data because our society produces a large amount of data. This is the data production in internet just in 1 second, and with this production of data, the volume is a challenge for the data integration. And it's not only the problem of the volume of data in data source, but also the number of data sources to integrate. We can reach hundreds of data sources. This is why we need an efficient multi-way join algorithm. And why we need a full outer join. This is an example of 3 data sources, and the result is G, the global view. If we perform an inner join, we will have only 1 row in the output. For this reason, we need a full outer join to get all row for the global view. And requirement for the join algorithm for Momis, it's a virtual approach. So we have to give a reactive response to the user, because it's interactive with the user. And another problem is the scalability of our join algorithm. And the solution proposed is a scalable online provenance join. We use the provenance information to perform a multiple way join in a single stage of join operation. This algorithm stores the data in a distributed hash map. As key, we have the join attributes, the value of join algorithm, and we store in the row the record with the sum with the sum join key value. And this join algorithm generates output progressively instead, so it generates output during the execution. The output generation it's performed when we have the complete data from all the data sources. In this example, we have 3 data sources, and there are no output generation until they arrive from the dataset D2. In this case, we have 2 rows for D1 data source and 1 row for D3. And when arrive the record from data source D2, we generate the first 2 rows, and when arrives additional records, we continue generate output. We perform a test of the performance of this algorithm with 15 synthetic datasets with different volume, 5 datasets with 10 million records, 5 with 30 million records, and 5 with 50 million records. In this way, we can perform multi-way join with 3, 4, and 5 data sources. And in these are results, and we compared our algorithm with the join of Spark SQL. In the first chart, we use a different number of data sources, and in second chart, we use different volume of data. In the y-axis, we have the execution time, and the red chart is Spark SQL, and the blue is our algorithm. And we can see we have a better performance with the increase of number of data sources and with the increase of volume of data. Now we move to the second join algorithm, the similarity join. Similarity join is a useful operator for data integration. Is used for data cleaning, and it's used to perform the duplicate detection and the record linkage. And from the definition, give 1 or more dataset and a similarity function and a threshold. The similarity join found all pair with a score higher to threshold when we apply the similarity function. With example, we have 2 records, A and B, and the Jacquard similarity as a similarity function and the threshold of 0.5. We can calculate the Jacquard similarity of A and B. The result is 0.67 and is higher than the threshold, so this pair A and B are in the output. The sample implementation of this join is given RS as dataset. We can perform a Cartesian product between 2 datasets to obtain all combination of pair between R and S. and we apply the similarity function to get the output. The problem of this algorithm is the complexity. If we have 1 millionth record in R and 1 millionth record in S, we have 1 million times 1 million pair to verify. And to optimize the similarity join, there are two strategies. The first is the optimization of the verify function, but this strategy is limited by the number of pair to verify. The second is reduce the number of useless comparison with filter to reduce this number, these filters must be more efficient than the verify function, and it must avoid discard the true positive pair. The start of the art of set similarity join is PP join. It uses three filters, and filter has length filter, prefix filter, and the positional filter. And our recent study, this is still one of best set similarity join, and MapReduce implementation of this join give this record of data. We have RID is the identifier of records, A is the prefix of record, and we map each token of prefix in this way. We have for the first record as key the token of prefix, and the value the RID and the record. We group by for the key, and group by the key, and we have in each block record with at least one prefix in common, one token prefix in common. And then for each block we perform Cartesian product and apply the filters of the positional filter and the length filter. This is the result of the similarity join. We have the record 1 joined to record 21 with the score of similarity of 0.5. And my contribution to this research is the implementation of PP join with Apache Spark. I use it as baseline for my to compare with my improvements. And the first improvement is avoid generation of duplicates, and the second is the implementation of a new filter. And the first problem, the generation of duplication. If we return to previous example, we generate two pair of 1 and 21. This is the reason is for these two records we have more than one token in common, and both generate a pair. In one we have a high number of pairs to eliminate the duplicates is a time-consuming operation. So the first improvement is avoid the generation of duplicate pair, and the first step is give a token ordering and order all prefix with this order. And the second step is when we generate generate the output pair, we generate only for the key attribute, the token which are common in with the last common token. And the second improvement is two-token filter. Given two records, x and y, and a Jacquard similarity function, and a treasure t, we can convert the Jacquard treasure to a overlap similarity treasure, and we can calculate the max number of elements that can be different between x and y. We increase this number by 2, and we have a new prefix to, with this number of tokens in x and y, we have at least 2 tokens common. And we test our algorithm with 4 datasets. The first dataset is a corpus of mails with 500,000 of emails, and the second is PubMed Abstract, a collection of medic publication abstracts, and the third and the fourth are citation from CTSR and DBLP. The second column is the number of rows in each dataset. Max is the max number of tokens in each row, and the mean is the mean number of tokens in each row of this dataset. AVG is the mean the mean number of tokens in each dataset. We perform self-join in the first 2 datasets. In this way, we can find the similar pair in the sum dataset. This is a duplicate detection task, and this with the third and the fourth dataset, we can perform a RS join. The result of our comparison, we have on y-axis the execution time of 3 algorithms. In blue is the basic version of PP join. In red is the improved version of PP join, and in yellow is the new join with the new filter. We can see with increase of number of workers, the performance is of improved version are always better than the original version of PP join. And the second chart is the performance of 3 algorithms with different threshold. These are tests on PubMed Abstract. We use only 20% of this dataset because pp-join go out of memory. And we can see the pp-join and the version which we use duplicate, we avoid duplicate are very similar. This is because the output pair are very small, so the difference between two algorithms is very small. And the third test is on citations. Also here we have better perform than the standard version of pp-join. And the last test, we test the scalability of tt-join on all PubMed abstract dataset. We use a different percent of volume of PubMed to test the scalability of tt-join with the volume. We test with 10%, 20% till 100%. And the second chart is with different number of different threshold. The blue is the test with 10 work nodes, and the red is 15 work nodes, and the yellow is 20 work nodes. Conclusion, in my PhD study, I studied and analyzed join algorithm in distributed environment. I propose improvements and new join algorithm for that data integration purpose, and demonstrate the performance of this algorithm. And this is the publication of PhD period. Thank you.
Nobody wants to ask questions. Thank you, Song. Now we have Luca. Can you come here, because we have. I think that we can begin with the presentation of the two doctors that was tutor Giorgio Vitetta, Francesca Facchini and Emilio Segnano.
So I want to introduce both.
Yes, both very quickly.
Very quickly. Okay. So the first presentation has been produced by Francesca Facchini. And Francesca Facchini is an example of PhD, of industrial PhD program, because she has been working for a private company, CPL Concordia, and doing her PhD studies at the same time. And I would say it's the first example of success which can be obtained through an industrial PhD program. So the company has been working in the field of smart metering for the new gas network in Italy. And this explains why the work done by Francesca is concerned the use of the VM-bus 169 megahertz wireless technology for gas metering, and also the use of new technologies for IoT applications which can operate on a long range, so LoRa and once again VM-bus. So this is about the first student, and the second student, Emilio Serignano, has been working on different topics which are of interest in vehicular applications. So in particular, filtering methods which can be used for data fusion in vehicular navigation, or smoothing, which can be used once again for data fusion in a number of applications. And then finally, power line communications for in-car communications, and the use of MIMO radars for a number of vehicular applications. So you can start the presentation.
Good morning, everybody. I am so sorry for not being there with you today. I am Francesca Facchini. My tutor is Professor Giorgio Matteo Vitetta, and the title of my thesis that I will present you today is Wireless Technologies for Smart Metering Applications. Just to give you a brief outline of the presentation, my thesis work was divided into three main phases. The first one concerning the prediction of propagation losses in the 169 MHz band. The second one concerning the comparison of wireless meter bus and LoRa technologies. And the third, the prediction of propagation losses in outdoor to indoor environments in the 868 MHz band. A brief introduction to the smart metering scenario. The Open Metering System Group has proposed the adoption of the wireless meter bus protocol for gas metering remote reading. And one of the available transmission mode in these technologies operates in the 169 MHz band, which has been recently relocated by the European Union to this specific kind of application. Right now, many devices have been already installed in Italy, and hopefully they will move in the next future also to Europe. A smart metering network is characterized by a star topology. You can see in this picture there is a data collector which forward the collected data to an informatic system, the central access system, and all the meter devices inside the network are connected to this data collector through a point-to-multipoint network which employs the wireless meter bus protocol. As I said before, we consider the two protocols in our project. The first one is the wireless meter bus in the 169 MHz band, which is the current standard for smart gas meters. It operates in a free portion of radio spectrum, is really robust against multipath fading and shadowing, and for this protocol, high transmission powers are allowed. On the other hand, we have the LoRa protocol operating in the 868 MHz band. It belongs to the low power wide area network family, and it is an emerging Internet of Things protocol. It is easy to implement. It presents an excellent receiver sensitivity, and it also operates in a free portion of radio spectrum. It is important to consider that all these projects have been carried out in an industrial PhD program, and in particular the first project concerning the wireless meter bus technology has been funded by the company CPL Concordia, whereas the projects concerning LoRa technology have been funded by the company Sagencom Italia. And we developed all the hardware related to transmitter and receiver devices, which we used to collect measurement points. So we can start by talking about the first project, the prediction of propagation losses in the 169 MHz band. Our goal was to develop a software tool for industrial use to predict the propagation losses in that band, but also to help the industrial technicians to properly place the data collectors inside a network on a given area. To do that, we decided to use machine learning techniques which allow us to overlook the physical aspects of radio propagation, and in particular we selected the support vector machines because it requires the optimization of few parameters, and this makes the training of industrial technicians easier, and it performs pretty well in the presence of small data sets. It is important to consider that this project can be divided in two main aspects. The first one is the prediction of the width of the coverage area given the position of the data collector, which is a classification problem. The other one is the prediction of the signal strength within it, which is a regression problem. Here is our hardware setup. You can see, of course, a transceiver on the transmitter side. We have, of course, another transceiver on the receiver side, but also a GPS receiver. And this is really important because this allows us to tag the measurement points during measurement campaigns. We selected 21 dBm as transmission power, so we considered a sort of worst case scenario, and the transmitter has been placed in a fixed outdoor location to simulate the data concentrator, and to collect points we move in its neighborhood driving on a car. We considered many scenarios, both in flat and hilly environments, and we collected approximately 27,000 measurement points. We used 3D digital maps, and thanks to those maps and our GPS coordinates, we could extract a 7-dimensional set of features, namely the transmitter receiver distance and angular deviation, the maximum and average height of blocking buildings, the portion of the radio links through buildings, the distance between transmitter and receiver and their closest building. These are for flat scenarios only. The transmitter receiver differential height and the portion through ground of the radio link, and these are only for hilly scenarios. The considered performance metrics for classification are accuracy, full-scale accuracy, which is the accuracy over a restrained interval of values close to the receiver sensitivity, and the false positives percentage. The considered performance metric for regression was root mean squared error. It should be noted that the developed software is able to evaluate also blind predictions, which are based on classification and regression models generated for environments different from the environment under test. Here are some numerical results. It is important to point out that there is no strong difference between blind and not blind scenarios, predictions, and you see those values into brackets are obtained by using neural networks as a comparison technique. And we can see a good level of accuracy and root mean squared error, also considering our kind of application, and it was really hard to collect data with a good level of accuracy and reliability. So these results are pretty satisfying. Our software is also able to provide a graphic output concerning, you see on the left, the width of the predicted coverage area of the single data collector, and on the right you see the signal strength map within those coverage area. We can move to the second project. the comparison of LoRa and wireless meter bus, the structure of the LoRa hardware setup is the same as that employed for wireless meter bus project. We selected a spreading factor of 7 and 20 dBm as a transmission power for LoRa, and we made measurements in an anechoic chamber to be sure that our transmitter was compliant with the ETSI regulation for the considered frequency. Our protocols have been compared in two distinct configurations. They have been considered operating at the same transmission power and operating at their maximum allowed transmission power, which is 20 dBm for LoRa and 30 dBm for wireless meter bus. Also here we collected measurement all in the city of Modena. Approximately 10,000 measurement points have been collected on the wall. And here you can see an example of a particular scenario. The red dots are the points inside the coverage area, whereas blue dots are the points outside of it. The performances of the two protocols have been considered in terms of packet error rate, and you can see there is no strong difference between the two protocols as long as the same transmission power, you have to consider 20-21 dBms, is considered. We saw scenarios where the transmitter was far from ground level and where transmitter was close to ground level, but there is no strong difference. On the other hand, as long as wireless meter bus at 30 dBm is concerned, we can see that LoRa is outperformed by wireless meter bus protocol, which is still the best technology for this kind of application. Nonetheless, LoRa keeps a really interesting protocol which has so many advantages, and it is interesting to investigate deeper how it behaves on other environments. So we can move to our third project, the outdoor to indoor environments in the 868 MHz band. So, as I said before, even though LoRa seems not to be the best option for outdoor meter reading, it has many advantages. So, for that reason, we have decided to move to a more restricted area. In particular, we considered the campus of engineering in the University of Modena, and we tried to make a preliminary assessment of outdoor to indoor propagation losses in that band and for that protocol. We tried to follow the same rules employed for the wireless meter bus project, so we considered support vector machine to generate prediction models, and we collected measurement points. And our aim was to build a software tool similar to that developed for the 169 MHz band. Our measurement campaign have been acquired by placing the transmitter outside and the receiver inside of the building, in front of the transmitter. And thanks to the availability of floor plans, we tried to follow two main rules in collecting points. We tried to collect at least 2 points per office, and to keep a uniform spatial sampling of 2 meters in corridors and other open spaces. The plans have been converted into a 24-bit bitmap format, and we extracted 9 numerical features. which has been computed for every radio link connecting the transmitter and the receiver position. So that they were the transmitter-receiver distance, the distance from transmitter and receiver and their closest obstruction on the link, the number of crossed roofs, ceilings and walls, and the portion through roofs, ceilings and walls. It is important to point out that this project is still on a preliminary phase. What we saw is that LoRa protocol is able to cover the entire area analyzed in our study. We collected 300 measurement points, and the RSSI values were generally well above the receiver sensitivity, and most of them lay in the -70s, -90 dBm interval. So we built only a regression model, because in this case classification had no sense, and we obtained a root mean squared error which were less than a dB. So this is a too optimistic result. We know that, but this is only a preliminary result. A larger dataset is needed to get a more reliable estimate of the radio coverage in that band. Nonetheless, we saw that LoRa protocol is able to operate reliably over medium-sized area and is suitable for every kind of application related to data collection. So just to resume a little bit, we provided some research results about radio technologies for smart gas metering. Our project was divided in 3 phases. The first one concerning a support vector machine-based method for the planning of a radio network deployed for smart metering and operating in the 169 MHz band. We developed a complete software tool for industrial use, which is able to carry out also blind prediction and is really helpful for industrial technicians to place properly the data collectors on a given area. The second one concerned the comparison of 2 radio protocols, so wireless meter bus and LoRa. They have been compared in terms of achievable coverage, and our results evidence that these protocols perform similarly at the same transmission power, whereas LoRa is outperformed by wireless meter bus as long as standard operation is considered. The third concerned a support vector machine-based method for assessing outdoor to indoor propagation losses for LoRa protocol. And our preliminary results showed that LoRa can reliably cover an entire building. But of course, future work should aim at collecting further measurements in different buildings of the University of Modena and Reggio Emilia, and why not also in industrial environments to assess the coverage capability of the LoRa protocol. This is the list of our publication on those topics. Thank you very much for your attention. Please feel free to contact me for any question. Thank you again and have a nice day.
Thank you. Francesca, that is very good, her work. And now we go to Emilio Segnano.
Non ce l'ho da Emilio.
We don't have this. So we can look after and we can ask the students of the 31 to begin their presentation. I know that Guido Borghi is asking, so we interleave live presentation with the videos because it's better for the audience. Guido Borghi, can you please come in?
Okay. Good morning, I'm Guido Borghi. My research topic is 3D vision for human-computer interaction, and my tutor is Professor Rita Cucchiara. My co-tutor is Professor Roberto Vezzani. There are 4 main elements in my research. The first element is the automotive contest. We all know that today automotive contest is a hot topic, especially in a field like autonomous driving, human-machine interaction, also called HMI, and driver assistance systems. The second element is artificial intelligence. In particular, we want to use computer vision algorithms and deep learning methods to create intelligence for the automotive context. The third element is depth images. A depth image is a particular type of image that contains information about the distance between an object inside the scene and the acquisition device, like the camera. And usually, depth images are acquired with infrared sensor. So if you use depth images in your project, in your system, you can achieve light invariance that is very important in the automotive context. And also, of course, you can have a 3D data. So in the automotive context, with the artificial intelligence methods, in particular computer vision algorithms, using as input depth images, we want to look inside the car to study the driver's face and head. In particular, we want to create model to estimate the head pose and the facial landmark position to study the driver attention inside the car during the driving activity. So this is the graphical user interface that we recently developed for a system to monitor the driver attention. On the left, you can see the 2 input, the RGB input, but also the depth image that I showed you before. And the second column has the head detection module. And the third part contains the head pose and facial landmark task. And the last column is dedicated to the study for the driver attention and the human-machine interaction. So, head detection module is built to understand where is the head inside an image. And the input is represented by depth images, and the output are the X and Y coordinates of the head center. You can see the task in the video on the right. And the second module is facial landmark estimation. Facial landmarks are salient points of a face, so for example, eye pupils, mouth corners, and so on. Input, as usual, depth images that you can see in the bottom corner on the left in the second video. And the output are the X and Y coordinates of the facial landmark points that you can see are reported as green circles on the face. In both images, in RGB image and also in depth image. Then we have the head pose estimation module. Head pose is the ability to infer the orientation of a person's head relative to the view of the camera. And this is the chart of the system that we propose and publish. And in particular, we use 3 types of inputs. The first input is the depth image, as usual. And the second input is called motion image, is an input based on the movement of pixel inside the image. And the third input is a gray level face reconstructed from the depth, thanks to a network called face from depth. And the output, there are 6 outputs of the system, 3 angles, 3 D angles called yaw, pitch, and roll, for both the head and the shoulder of the driver. Then, I recently spent 4 months in Stanford University, and I implement algorithm for the head pose estimation task and also for the fine gaze prediction for the social navigation of a little robot called Jackrabbit that you can see on the right. And the main question is the robot facing a person? So we want to understand if the robot is facing a person, so if the robot is engaged in a conversation or in a social interaction. And in the video you can see the green light when the user is facing the sensor placed on the top of the robot, and the red light when the user doesn't see the robot. Future work. My future work are about hand detection and tracking in the automotive context as well, and also driver attention analysis. I would like to complete my analysis about driver's attention using the information that you have seen before, so head pose estimation and facial landmark, in particular the state of the eyes of the driver. And this is a list of my publication, and I thank you for your attention.
Thank you, Guido. Do you have questions? Because Guido is entering in his third year of doctorate, so if you have some suggestion to conduct or some questions, no, after. Thank you. Luca, passiamo all'esame. We make another video now. Marco Lasagni, the tutor, Professor Pavan, want to introduce.
Marco Lasagni is a PhD student who worked on energy harvesting and sensor systems, exploiting heterogeneous technologies. The work is it's very interesting because he was trying to do some low-cost new technologies for industrial application. During his work, he's been involved also in the creation of a startup company that actually placed second, I think, during the national prize on innovation we hosted here last year. So that was a long effort and a heavy effort for him, and then he couldn't probably publish that much. At the end of the day, he doesn't have that many publications, and that is probably due to the fact that he's been involved in the spin-off creation as well. So the work is very interesting for the possible industrial low-cost industrial application that can be achieved out of that. Thank you.
Good morning to everyone. I am Marco Lasagni. I apologize for the absence, but in this moment I have an important work commitment. The title of my presentation is Energy Harvesting and Sensor Systems, Exploiting Heterogeneous Technologies. During my PhD I have worked about three main topics. Firstly, I work on the development of transducers exploiting the triboelectric effect to harvest energy from mechanical vibration. Secondly, I design and realize an ultra-low voltage DC-DC converter to boost the low voltage generated by low thermal gradient. Finally, I design and realize an ultra-low voltage and power displacement sensor exploiting eddy current effect. The growth of wireless sensor network is nowadays limited by the battery capacity and their high maintenance and replacement cost. A solution is an unlimited power source. In order to reach this result, a solution can be the energy harvesting to prolong the battery lifetime and have a lower power consumption sensor. The operating principle of triboelectric device is based on the combination of contact electrification and electrostatic induction. By contacting two dissimilar materials, two opposite electrostatic charges are created on the surfaces, plus and minus sigma in the figure. Consequently, if the surfaces are separated, a voltage difference can be generated, driving a current in a closed circuit. The figure shows the basic representation of the contact mode triboelectric device. This principle can be used to harvest energy, for example, from mechanical impact. The devices were realized through an easy in-house fabrication processes by a manual deposition of commercial silicone on the metal plate used for the contact, and the sample structure of the device is resemble a metal insulator metal with two dielectric layers, which reference to the device structure shown in the figure. Different device with different thicknesses and dielectric material was realized. In order to characterize the prototype, I have realized an ad hoc setup. It is comprised of a laser vibrometer, an electromagnetic shaker, and an impact hammer and oscilloscope. The setup allows to measure for each test the output voltage generated by the device when the two triboelectric layers are repetitively put in contact with a given force, and the relative displacement, the relative velocity, and the impact force between the two dielectric layers. Let's see the output voltage waveform generated by the device at different contact forces. The figures show that the output voltage and then the power depend on the force, on the contact force. This slide shows the classic model, so-called voltage charge displacement relationship. In this model, the output voltage generated between the two device contacts and on an external load is given by the contribution of two terms. The first is the triboelectric source, depending on the distance between the two layers, X, that vary accordingly with the mechanical stimulus, and depending by the sigma. The second term is the voltage drop on the equivalent device capacitance. The model considers an instantaneous contact time and do not take into account the effect of the contact force between the two layers, which influences the generated voltage as shown in the previous slide. We include the role of the force by considering that the charge density sigma depends not only on the properties of the dielectric materials but also on the contact force. The empirical relationship expressed in two direct contour has been obtained by applying to larger scale the approach proposed by Professor Matsusaka in 4 to describe the triboelectric charge mechanism of a single particle hitting a wall. In the model, n is the number of impacts that are assumed large enough to approximate the steady-state condition for its forces. Sigma 0 and sigma infinite are the initial and the saturation value of the surface charge density. C is a coefficient that expresses the velocity to reach the saturation, and is obtained by an automatic iterative procedure implemented in MATLAB. The obtained sigma in function of the force can be directly included in the classic model. Let's see the comparison between the measured output voltage on the prototype at different forces and the corresponding output voltage simulated by means of the proposed model. A very good agreement between simulation and measure is shown, supporting the validity of the proposed model. The result confirms, in fact, that different from the assumption of the previous model, the impact force produces a variation of sigma. Let's see an application of the triboelectric effect as flow meter sensor. All the mechanical parts have been realized in ABS using a commercial 3D printer. The system is comprised of two main parts. The first one, the main body, resembles the classic structure of impeller-based flow meter, while the second one includes the triboelectric transducer. Each sector S1, S2, S3 and S4, which the impeller blade form a single triboelectric device operating in sliding mode. By changing the capacity coupling between S- and S+ for each sector, it is possible to obtain a voltage generation across the two terminals. The variation of capacitance can be easily obtained by exploiting the rotation of the triboelectric impeller as a result of the flow in the structure, of the airflow in the structure. The prototype has been characterized by using the setup shown figure. To validate the proposed solution, we use the airflow provided by a portable air compressor. Both the output voltage generated by our prototype and the output signal of the reference flow meter are acquired with an oscilloscope. Let's see the comparison between the output signal of the reference flow meter in the first row and the output voltage generated by our prototype in the second row under constant and variable airflow condition. Different from the classic flow meter, our prototype is self-powered. It is possible to estimate the amount of material flowing through the device by measuring the frequency of the voltage pulses generated by the device. The result showed a very good agreement between the commercial reference flow meter and our prototype. The second part of my presentation is energy harvesting exploiting thermal gradient. The core of thermal energy harvesting is the thermoelectric generator formed by a large number of thermocouples connected in series. Applying a thermal gradient between the hot and the cold side of a thermocouple, a voltage difference can be generated. A commercial thermoelectric generator can generate voltage about 20 mV with a thermal gradient of 2 degrees. The slide shows the state-of-the-art DC-DC converter for low input voltage. It is based on the Armstrong oscillator topology, followed by a charge pump rectifier. The oscillator is comprised of a step-up transformer, a depletion MOSFET in charge to start the oscillation, and an enhancement MOSFET in charge to transfer the power between the input and the output. The main limitation is the minimum input voltage for correct operation, that is above 20 mV. This imposes an important limitation to the maximum thermal energy that can be harvested with a tag. In order to reduce the minimum startup voltage while maintaining a good efficiency, I have proposed a new architecture which allows to operate with an input voltage as low as 11 mV. The circuit consists of 5 functional blocks as are shown in figure. The two important core of the circuit are the ULVO, ultra low voltage oscillator, in charge to start up the circuit, and the VBO, voltage biased oscillator, in charge to transfer the power between the input and the output. The ULVO is designed to oscillate with low DC input voltage lower than 10 mV. The key aspects of the ULVO design are the replacements of the depletion MOSFET with a zero threshold MOSFET, and the introduction of an inductor in series with the secondary winding of the transformers. The LDO have two important functions. The first one is to regulate the output voltage of the previous stage to the optimal value for the current biasing of the transistor of the VBO. And the second function is to avoid the squagging phenomenon, which shifts the DC bias point, suppressing the oscillator for a period of time. The VBO function is to maximize the energy conversion and transfer between the source and the output. It is designed using a high current capability MOSFET. The DC voltage waveform generated by the VBO is boosted and rectified by the final stage, which act on both the positive and negative parts of the waveform. Let's see some results. In the left figure, let's see the charge time in function of the input voltage at two different output voltage, 2.1 and 3 volt, both suitable to power microprocessor or wireless sensor node, for example. With an input voltage about 11 millivolt, the time needed to charge an equivalent 500 microfarad completed discharge capacitor is 8-9 minutes. Around 12 millivolt input voltage, the converter needs only 4 minutes. The peak efficiency is about 44%, confirming the goodness of the proposed solution. The converter, powered by a tag, was tested with an input thermal gradient between 0.6 to 4 degrees, and they can support low power pulsed load applications such as a low duty cycle BLE transmission with a transmission burst rate over the range 0.08 to 3.4 Hz, depending on the thermal gradient. The final part of the presentation is the low power displacement sensor exploiting eddy current. The demand of the displacement sensor is rapidly increasing thanks to the micrometric resolution and the intrinsic capability to estimate multiple quantities such as pressure, acceleration, vibration. But the main limitation of these sensors are related to the power consumption above than 1 milliwatt that limit their application in a real-time battery power system. In order to overcome the limitation related to the power consumption, the purpose of this work was to demonstrate that a 10 micrometric resolution eddy current sensor can be achieved with a power consumption lower than 200 microwatt. Let's see in the figure the equivalent circuit of an eddy current sensor. It is comprised of an AC tank that is excited by an external AC current. The magnetic field around the coil is the sensing field. Once a metal target enters the sensing field, eddy current are induced on its surface. The interaction with the target results in a variation of the equivalent sensor impedance at the coil terminal, proportional to the position of the target. In order to compensate for the tank loss accounted to the resistive part of the coil, an equivalent negative resistance is needed. The negative resistance can be obtained by considering the Pierce oscillator as depicted in the left figure. The circuit is comprised of an active device, a MOSFET, a passive network forming the sensor coil, the capacitance C1 and C2 forming which the coil, the LC tank, and the inductor L bias for the bias of the circuit. The key of the design is the high transconductance at low level voltage allowed by a zero threshold MOSFET. This allows us lowering the voltage supply, consequently reducing the power consumption of the circuit. Let's see the output voltage over the micrometric movement of the target with respect to the coil. The result confirmed the goodness of the proposed solution, in fact, with a very low power consumption, lower than 40 microwatt. The output voltage is proportional to the displacement in the whole displacement range 0.5 millimeters. And there's a good linearity between the displacement and the output voltage in the displacement range 0.2 millimeters. Let's see now the input power and resolution according to different supply voltage value into the displacement range 0.500 micrometer. Under equivalent displacement condition, an increase of the supplied voltage and of the supplied power improves the achievable resolution. Specifically in the displacement range, in the considered displacement range, a resolution about 3 micrometer can be achieved with very low input voltage, 200 milliwatt, and no power consumption, lower than 200 microwatt. Concluding, I have worked about energy harvesting and sensor exploiting triboelectric effect. I have proposed new low-cost contact mode triboelectric devices designed to harvest energy from mechanical impact. Then I have proposed a new model for a triboelectric effect, including the effect of the impact force. And then I propose a self-powered ultra-low-cost triboelectric flow meter. Then I have worked about energy harvesting exploiting thermal gradient. I have proposed a new low-voltage DC-DC converter able to boost 11 millivolt input voltage to 2.1 volt. The converter reduced the conversion startup volt of the traditional and commercial DC-DC converter by a factor 2. The converter is powered by a tag with thermal gradient varying from 0.6 to 5 degree, can support low duty cycle BLE transmission. Then I have proposed and designed a new low power displacement sensor exploiting eddy current, able to reach a resolution better than 10 micrometer with a very low power consumption in a displacement range of 2 millimeters. Thank you for the attention.
We alternate the presentation. Now the next presentation is Giuseppe Fiameni, Cycle 31.
Hi, good morning. I'm Giuseppe Fiameni. I'm supervised by Professoressa Bergamaschi Sonia, and I'm doing a PhD on this topic, which is processing large scientific data sets using big data technology. I actually work in Cineca. I'm also supervised by Dr. Sanzio Bassini, who is the director of the High Performance Computing Department. I picked up 3 topics for the presentation today of the activities that I've been working on over the last year. So the first is the profiling and optimization of widely used big data and deep learning frameworks on high performance computing facilities and resources. The possibility to use MapReduce technology to improve analysis of climate data, and the contribution to a pan-European infrastructure for the provisioning of interactive computing for the human brain project. I will share a few words about that. So the first activity that I worked on, so the idea was to study how deep learning frameworks can scale on classic HPC systems, because we observed a very waste of resources, especially when using with new big data technologies and tools and library. We would like to understand how far they could really exploit hardware capabilities. And we prepared this work, which is a performance study of machine and deep learning frameworks on Cineca HPC systems. We took a benchmark of most common neural networks, and we had the performance study on the systems. that we have now available. These are the description of the machines that we have been using. We used hyperscaling processors such as Intel Broadwell or Night Landing with 64 cores per node and plus up to 3,600 nodes using MCD RAM. So Broadwell, Night Landing, and Aswell, and including 2 NVIDIA GPU cards for deep learning workloads. So the preliminary results of this study, I'm plotting here what the overfit network performs on these systems. Unlikely I don't have a laser pointer here, but this just to show. I mean, there is a comparison of the network comparing with the common used framework. We used Caffe, Intel, TensorFlow, Theano, Intel, and Neon over 2 Broadwell per node Night Landing, Key 80, which is a GPU, and P100, which is a GPU NVIDIA Pascal. Using those on the tops are the block sites. So this is how an overfit network perform. You can see how it can vary in performance. These are the images per second that can be processed. So if you take a P100 using Neon, which is an Intel framework, you can process up to 1,100 images per second. It's a very performing card. The paper includes other benchmarks, including also machine learning tools. We had studies for Apache Spark and Python R libraries and H2O, which is very famous framework. And the studies are included in a paper that I have the link at the end. So the second topic that I would like to share today is work that we have been doing with the International Center for Theoretical Physics in Trieste and the OGS Center for Oceanographic Studies. So the idea was to use a big data tool to process climate data. So the goal is to, since the amount of collected data is increasing largely, and due to high accuracy of instruments and number of sensors that are put on the fields, the idea is to integrate all these sources and try to perform near real-time processing to detect insights as data get in. If anything bad is happening, or if you need to monitor a specific situation, we developed a couple of tools that I'm showing you to process very large data sets. The goal is that, I have a problem here, okay, no, it's working fine. If you typically take a library in this domain, which is called Iris, you can easily manipulate a climate model, which is based on SDF file, but as the data increase, you might encounter a memory problem, because usually you don't have enough memory to store chunks of data in your systems. So the idea was to use Apache Hadoop to process this data, because it can easily distribute the load on a system and say differentiate the capsule, the logic of your application. The problem, unlikely, is that Apache Hadoop works very well with text files, with the ASCII files. Chop data brutally. You don't have any way to tell Apache which way you want to distribute your data sets. It's not semantic aware, of course. It's based on Java, and it's a batch way to launch your job. But unlikely, the climate world is using netcdf files, which is based on binary. It's based on ASCII header and binary payload. They are monolithic data, so you need to, if you want to calculate the average of a temperature, for instance, you need to understand all the volume of the column where the data is located to. Java is not a very common programming language in that domain, and it's basically interactive, because you want to manipulate the data interactively. So we developed these two tools, which are called Pipistrello. We developed two tools which are called Pipistrello and Tina. It's very funny names. Pipistrello is a tool that is able to execute MapReduce jobs on binary files because it is able to interact with the HDFS to check where the physical file is and retrieve it, and let's say get the data without using the ASCII overhead. And Tina is a lightweight Python library that's sitting on top of Iris to handle NetCDF file, Snakebite, to efficiently communicate with the Hadoop file system, Pipistrello to launch the job, can manipulate the data, the climate data, using the combination of all these tools. So the goal was to use Apache Hadoop to manipulate climate change models, and we presented the results of this work in this conference last year. So we are still working on the tools. I'm still working on partially on those, and I hope to be able to release a stable release by let's say this summer. Finally, this is a very aside work. I'm part of the Human Brain project, where I contribute to the development of the pan-European infrastructure for the supercomputing. The idea is to deliver a multi-purpose infrastructure for innovative studies. I'm one of the architects of this activity. And we are working to set up these systems, the combination of these systems in Europe, where Italy is represented by Cineca, the center where I share this PhD with, and include Barcelona, CA, Jülich, and CSCS in Switzerland, and to provide a seamless access to all these systems to execute neuromorphics workloads on top. These are the list of publications for the last year, I think, and yeah, the international conferences, the participation to national, international workshops, and the training, the teaching and training activities. And that ends my presentation. Thanks.
Giuseppe, for your very interesting presentation. And now we have another video, because we have live and video, and I ask someone who can try to connect with Japan, with Stefano Aletto, because the next will be his presentation, and we have to contact him by Skype. Yes. This is the last presentation of the doctor. It is Fabrizio Balducci, Computer Science and Engineering, and we have a video.
Good morning. My name is Fabrizio Balducci, and my PhD thesis is about effective and interactive evaluation of multimedia data. Multimedia data are linked to human senses. So we have the sight, the hearing, the tactile, and the movement. And interactive multimedia are virtual worlds or video games that nowadays are cheap and controlled simulation environments for experiments for gathering synthetic data. The first research question is how objectively evaluate a virtual world and its activities, since the player is unreliable. Some forget details and is no objective judgments. So we have to use physiological data with advanced sensors like the EEG, ECG and EMG. Research question number 2, how to obtain and manage this data. The answer is the brain-computer interface, like the Emotive Epoch headset that gather numeric data, is cheap and non-invasive. And we use some tools like a role-playing virtual world, the video game Neverwinter 92, and machine learning classification techniques. The third research question is how measure the interactive experience with this data, and the answer is the active ludo paradigm that uses scientific methodologies, so we can exploit formal design guidelines to describe the activities. Emotions and affects are short-time peak, while mood state or an affective state is a continuous lasting emotional trend. So we have to consider the emotive black box classified data, which comes from the emotive epoch, that are punctual values. And we can design and develop two affective game levels, the boredom and the flow, and with the formal design guidelines that are specific for the feature of a role-playing game zen and gameplay, with dialogues, exploration, allies, and so on. So for the boredom game level, we have, for example, minimum challenge and constant difficulty for the first, and the third guidelines is about health and ammunition always at the maximum. For the flow, we have the first guidelines, diversified environmental structures, and the fifth, well-defined and satisfactory goals. The data source are two, the events log and the affective log, and they are synchronized with the timestamp. So we have the local and global evaluation. Since we have to face three problems, the data logs are very long, the AG data greatly change over time, and the activities are heterogeneous with various time duration. So we have to split the logs to take some semantic units that have to be summarized with the AG emotion data, and the numeric feature are the data that summarize one single activity. We have 5 features, and this feature can be used in the experimental study, which involves 19 academic students, 12 male and 6 female subjects that plays both game levels. The machine learning technique for the global evaluation of the group, the sequence of all the activities are the linear SVM, the radial SVM, and the decision trees technique. So we can see the classification results from which decision trees reaches best performance of 96% for classification. So the activities are well split in the feature space, and they are enough to automatically differentiate the two game affective levels. Some consideration from this work: the guidelines are effective to manipulate emotions and induce affective moods. Virtual worlds are valid for experimental environment. Brainwaves are suitable for affective ludology experiments, and moreover, this method is an effective evaluation framework, which is easily extendable to real-world evaluations. The second topic of my thesis is about the skin lesion detection on dermoscopic medical images. So we have an architecture for a medical image management system. We have a dataset of lesion images primitive features from the annotation, manual annotation, and the derived features like contours, shapes, and intersections. We developed an annotation tools following the principles of usability and human-computer interaction, and this tool was evaluated with questionnaires. We have a processing phase of the thick air removing, which uses the generalized grayscale morphological closing operation with the detection and the replacement step of these airs from the dermoscopic images. And for lesion detection, we have two techniques: the threshold with pixel mask and the color clustering with pixel tolerance, since we have to exploit the peculiar structure of a dermoscopic image, the large black frame, the lesion localized at the center, and the circular white halo. For the color clustering, we have the pixel tolerance, since we have to discriminate if a pixel is a lesion or the bright skin. And for experimental results, we have two datasets with 17 images, which are hard for their features like color, hairs, and structure. We have two datasets, the original and the thick are removed. And for each image, we have the ground truth, which is the area that comes from the manual annotation made by experts. So we can intersect this ground truth area with the detected pixels, and we can notice that the color clustering reaches the best performance. In fact, the precision is 93% and the F1 score is 83%. With this example, we have the original on the dataset 1 and the removed dataset for the color clustering pixel tolerance. We have the deep learning approach. The easy dataset is used to train a deep neural network, and the dataset is constituted with 2000 training, 150 validation, and 600 test images, each with the ground truth annotation. The Deep Lab convolutional neural network model is used, developed for the segmentation task on real-world images, has been retrained for skin lesion analysis. The evaluation metrics are the Jacquard index and the Dice coefficient, and we can notice that the convolutional encoder-decoder, which exploits the neural network for the segmentation, and DeepLab introduced the atrocious filters. This is the list of my publications, and thanks for the attention.
Hello everybody, I am Stefano Letto, and in this video I will describe you the work I did during my 3 years of PhD with the title Visual Understanding from an Egocentric Perspective. The first topic I will describe you is how to exploit egocentric vision for understanding social relationships between people. The goal here is to understand what groups of people are present in a scene and how different people are interacting with each other. This is especially challenging in egocentric vision due to, for example, facet motions that can cause severe motion blur, or because of the ability of the user to travel from inside to outdoor, and this causes severe lighting changes that needs to be dealt with. Then I will describe you my work about the enhancing of cultural experiences. Here the goal is to use wearable devices to enhance the user cultural experiences by, for example, providing information about the artworks or the monuments that it's looking at. Here, the main challenges are the extraction of common computer vision features that are impossible to extract when there is severe motion blur. Another challenge is to be able to provide such information during all times of day. For example, it is possible for a user to visit the cathedral during the night, and the system must work also during the night. Finally, I will describe you my work on the topic of understanding the egocentric motion of a moving vehicle. If you think about it, automotive is just a specific case of egocentric vision where the perspective is the one of a car-mounted camera. In this field, the main challenges are, the first one is that it's extremely expensive to acquire ground truth information for the optical flow. In this image you can see a flow field, a ground truth flow field from the ICT dataset, and you can see that it's extremely sparse. Also, it has been acquired using a LiDAR device, which is very expensive. Another main challenge is that automotive videos usually have very low entropy data. That means that most of what you're looking at is not extremely meaningful. So for example, you want to catch that one pedestrian that occupies a small portion of the scene, but it's very important. So let's start with the understanding of social relationships. As we mentioned, here the goal is to recognize a group of people interacting with each other. So for example, there's a scene, there's multiple people, and our algorithm aims at understanding who's interacting with whom. Also, it aims at understanding what we call social relevance of individuals. That means, what are the individuals that the user is most interested in? Here the main challenges and requirements are that we need to be able to reliably detect and track people, and we also need to be able to reliably extract what we call socially relevant features, namely at-post estimation and distance estimation. To do this, we develop a system that features two main components. The first one is a neural network that estimates the visual saliency of the scene in what we call the socially attentive model. So the goal of this part is to understand what are the most relevant people in the scene so that we can build a social relevance graph that tells us who are the most important people for the user. The second part relies on a more traditional computer vision pipeline and starts with tracking and estimating the facial landmarks of each individual in the scene. Using this information, we built an at-post classification method that estimates what the individual people are looking at and performs their at-post estimation. Also, it estimates their 3D localization, so it finds out in a 3D world where they're standing. Finally, we use this feature in a structural SVM classification framework that learns how to weight these features and build a clustering map that gives us the social groups. Just to give you an example on how the method works, in this video you can see that different people are correctly detected and their 3D model is built, and you can see the triangles indicating their orientation. Also, you can see that the different colors indicate their belonging to different groups. Let's now talk about how to exploit wearable devices to enhance user cultural experiences. The goal here is to exploit some source of information, in this case a 3D model of a building with highlighted details, to respond to a user query asking for information about each single detail. The first step is going to be the retrieval of such details. The first challenge in performing such retrieval is to be able to do it in real time. Traditionally, this kind of algorithm is very slow. So what we develop here is an algorithm that, given a query image acquired from the user, it computes SIP descriptors and organizes them in a KD tree structure. In order to keep the tree balanced, you need 2 to the power of the dimensionality of your descriptor, and in this case, shift descriptors have 120 dimensions, which is a lot. So you would need 2 to the power of 128 data points in order to keep the tree balanced, and this is definitely not feasible. So in order to be able to exploit the properties of KD trees, we decided to reduce the dimensionality of the shift descriptors using principal component analysis and k-means clustering. So we organized the descriptors by reducing their dimensionality and by quantizing them using bag-of-word techniques. This allows us to perform the 2D to 3D correspondence search in a very fast manner. So just to give you some quantitative data about what we just described, using a brute force approach to perform the 2D to 3D matching takes almost 2000 seconds. And no amount of hardware parallelization will help you here. We experimented by using brute force parallelized on CPUs and GPUs, and while you can see that the time decreases, it's still not satisfactory, because using the combination of KD trees and GPU parallelization, you can get down to 500 seconds, but this is not sufficient. While our technique, using a combination of bag-of-word quantization and principal component analysis to reduce the dimensionality of the shift descriptors, gets the result in roughly half a second, which is an acceptable time for an interactive application. Then we need to be able to deal with the changes in the light condition that can arise when performing a visit during the night. Here the main issues are that shift descriptors do not reliably work during the night. There is this problem called orientation flip, where the descriptors look the same but their orientation is changed and they cannot be reliably matched to each other. So we need to develop something that allows the user to match a query acquired during the night to a 3D model built during the day. Our main idea here is to build a novel embedding space that takes into account local descriptors, their spatial arrangement, and their temporal robustness. So the overall idea is we extract a shift patch centered on a key point, and we also extract a region around it. And in this region, we perform a dense sampling of shift descriptors, and we build a context descriptor that is based on the covariance matrices of the shift descriptors. Then we introduce temporal consistency by tracking each individual shift key point back and forward in time. And if the tracking is successful, we deem the schema reliable, otherwise we eliminated it. So far we described techniques to extract the architectural details from a 3D model in real time and during the night. But how are those details labeled on the 3D model? You can see in this image an example of a labeled 3D model, and in this case we had a grad student manually annotate every single 3D point of all the details. You can imagine that this is not scalable, as it takes a lot of time to perform this action. So our goal here is to develop an algorithm that is capable of unsupervised detail discovery. That is, it's able to find the details without manual intervention. Just on a side note, the work I will describe you here won the Best Paper Award at a conference. Given a 3D model, in order to extract the relevant details, the first step is to compute features, such as the difference of normals. The difference of normals is a feature that, given a 3D point and two surfaces taken at different radiuses around this 3D point, gives you a measure of the planarity of the zone. So the difference of normals will be small when there is a planar zone, and it will be high when the two normals are not close to each other, meaning that the two surfaces of two different radiuses are not planar. And this is a descriptor of the planarity of the zone. Here the assumption is that the relevant detail is something that is not planar, for example, a statue, a bas-relief. Obviously, this wouldn't work for a museum where you were looking at pictures. Once you have computed these features, you need to find out which points actually correspond to a detail. So by selecting a random point, we start the expansion of a 3D sphere in an algorithm that is similar to a float field algorithm. So we expand this 3D sphere in the model, and we start clustering together points belonging to the same detail when the sphere expansions encounters them. We stop expanding the sphere when it stops encountering points for a while, and this while is computed using a threshold. So the sphere expands and highlights all the relevant details, and this image, you can see that to each 3D point cloud, it corresponds a series of images that created those 3D points, and they represent all the relevant details. Finally, let's talk about how to extract the egocentric motion of a car moving on a street. Here, optical flow is an extremely important information for lots of computer vision tasks, such as object detection, tracking, or collision prediction, or trajectory estimation, just to name a few. In order to extract the motion flow, we rely on a deep learning algorithm that is composed of a network that features two main components. The first one is what we call ego motion network. It's a small-sized network that, given the pair of images as input, it estimates a global transformation that approximates an homography transformation of a car zooming on the street when it's going forward, or a rotation and translation when it's, for example, taking a turn. The second part of the network, it's a refinement network, takes this initial estimation and refines it by accounting for the motion of individual objects. Finally, this is a list of my publications. I thank you for your attention, and I welcome any questions. Feel free to email me with questions or suggestions. Thank you very much.
Magnotta is the first industrial doctorate student of our doctorate. We have Francesca Facchini in high apprenticeship, alto apprendistato, but the first industrial, it is a person enrolled by a company which getting his doctorate is Luca Magnotta. Please, Luca.
Thank you. Good morning, I'm Luca Magnotta. I'm here to, you can hear? I'm here to describe briefly my research activity for my doctorate. In the doctorate in industrial application of ICT, as titled Big Data Integration, and I have as a tutor Professor Sonia Bergamaschi, and as industrial co-tutor PhD Mirko Orsini, that is the CEO of Data River. Why am I doing this doctorate? Because I'm the supervisor of the unit operation of data integration in Data River SRL. That is a company that is specialized in designing and developing solutions for clinical data management and data integration to solve the problem of inconsistency, heterogeneity, and quality of data to be integrated. To do this, in collaboration with the DB group of Modena and Reggio Emilia, we created the Momicchioli system, that is a system that aggregates in a semi-automatic way data coming from heterogeneous data sources that can be structured or unstructured, for example, databases, spreadsheet, open data, and so they can be distributed all over the internet. So, in my research, I had two topics that are big data integration, schema label normalization, and business intelligence tools for integrated data. For the first topic, I'm also having as goal to bring MOMIS to the big data integration. For example, we are using MOMIS in an industrial context where we have IoT devices, sensor used in tile industries that are devices that produce millions and millions of data. The second topic I'm approaching in my doctorate is the lexical annotation, the schema level normalization that is linked to the lexical annotation and mapping discovery. Because in a system that performs data integration, is important to find in a semi-automatic way the meanings of the data elements that are inside my sources. The elements are the class and the attribute. So, for example, if my source is an Excel sheet, the class is the sheet and its attributes are the columns, to be clear. And in integration, the meanings have to be found using as a reference a thesaurus or an ontology. The problem is that these elements can be non-dictionary word, so an automatic system can fail because this word can be abbreviation or acronyms or also compound nouns. So it's important to perform a schema level normalization. And in MOMIS it's present a tool that we call the norms tool that performs the schema label normalization and annotation. So from these words it is able to find their meanings. And in my research activity I'm improving the normalization process in order to have a better normalization that is context aware. On the other hand, I also analyzed other open source frameworks like Stroma and Coma to evaluate how schema label normalization can be improved using a semantic repository that integrates several knowledge sources. For example, we are using WordNet, UMLS, ConceptNet, or also DBpedia. The last topic of my research is the development of business intelligence tools for integrated data. All the amount of data that are integrated must be visualized in a simple way that can be understandable and interactive. So, in using the business intelligence tools that uses the data collected to find KPIs, key performance indicators, that are, for example, charts, maps, or tables. Charts that can be line charts, pie charts, area charts. And in my research, I'm using the MOMIS dashboard, that is a BI tool designed to work together with MOMIS, and I'm using it in a big data analysis context. The final goal is to make it a powerful tool also for data monitoring in IoT and IoMT context, and a data prediction, a tool for maintenance and predictive maintenance. And the challenge in my work is to handle this large amount of data, trying to satisfy the needs to be easy, understandable, accurate, and responsive. And these are my activity. These are the references of the tool I've mentioned and the conference I participated in this year. Thank you for your attention.
Thank you. Now we have Paolo Latorraca, and then we will have the last video from Luca Di Cecilia. And no, the last video, but now we go out and look at all the poster of the youngest student. Okay?
Good morning. My name is Paolo Latorraca, and today I would like to present you my presentation, my PhD activity on the development of the thermoacoustic loudspeaker technology. Well, a thermoacoustic loudspeaker is a transducer that converts an electrical signal into an acoustic signal that in the end is sound, and achieve this exploiting the thermoacoustic principle. And we will see what that means. The structure of a thermoacoustic loudspeaker is very simple. It's a two-layer device. The first layer, called the substrate, is electrical insulating material over which is deposited a thin layer of conductive material and called the active film or active layer. Okay, and this is, since this has to be extremely thin in the order of the nanometers, this must be fabricated using spray coating technique, sputtering, or vapor deposition techniques. For what concerning the underlying physics, two atomic transductions can be recognized in this device. The first is the Joule-heating, okay, very common phenomena, in which the power dissipation is fully converted into a heat flow in the device. This heat flow is then redistributed, subdivided between the air and the substrate. The heat injection into the air leads to the second transduction, that is the real thermoacoustic transduction. And in the air, the heat injection makes the air itself expand, leading to the generation of a pressure wave. So, in order to improve this technology, I adopted a model-driven development. So at first I developed an analytical, physical-based model of the thermoacoustic loudspeakers, including the Joule-heating effect, the subdivision of the heat flow inside the device, and considering the coupling of the pressure field and the temperature field. That is the key concept for the thermoacoustic phenomena. And at the end, I obtained this electroacoustic model, which, okay, we won't spend much time on this. Just if you inspect this model, trust me, you will find two main ways to improve the efficiency of this device. The first, that is the most common way used and found in literature, is to reduce the heat capacity of the active film, and this is why it is usually made as thin as possible. From this model, another way to improve the efficiency arises, and is the minimization of this ratio. That is the ratio between the thermal effusivity of the air and the sum of the thermal effusivity of air and substrate. At the end of the day, this means that the efficiency of the device can be maximized if the thermal effusivity of the substrate is reduced. Okay, this can be better appreciated probably with this. No, it can be appreciated at all. By the way, trust me that if you reduce the substrate thermal effusivity, you will get a higher efficiency. Follow the dots, please. Okay, interpolate. So I made a research on the thermophysical properties of the materials, the most common materials found nowadays, and I find out that the best materials for me to improve the efficiency, so the materials with the lowest thermal effusivity, are the porous materials, such as polymeric foams and the aerogels. Since the aerogels have slightly better properties than the polymeric foams, I decided to use such materials to fabricate some sample. So in collaboration with the University of Munich and the EMPA, that is a research center, a Swiss research center that is actively working on aerogel materials, we fabricated these samples that are much more pink in reality. But yeah, it's a silica aerogel sample with a gold active layer of 100 nanometer of thickness. And in comparison with other samples that we fabricated previously, using non-optimized substrate, we obtain a much higher efficiency, 30 dBs, 20 to 30 dBs of gain efficiency. So yeah, the aerogel is a very promising material for this kind of task, but it is also extremely fragile. So we are still working with EMPA to find a solution to this problem, but the fragility is like one of the key property of the aerogels. And I hope to find obtain similar results using the polymeric foams that have a much better behavior from a mechanical point of view. And that's it. Thank you for your attention.
Thank you. Now we have the video
Posso
of Luca di Cecilia.
Avevo una domanda.
Ah, a question.
Just a curiosity. What's roughly the temperature of the substrate?
It depends on the temperature depends on the SPL, on the sound level that you want to achieve. At the moment, I achieved quite low pressure levels, around 50 to 60 dBs. And this corresponds to a temperature that is in the order of 100 degrees, which is quite high, without using any heat sink or stuff like this. Just the last week, I started using heat sinks because I want to test how high can we get, okay? And I'm working on this also. No problem.
The video of Luca di Cecilia, and after each student of 32 comes out close to his poster, because we make a video also of the poster and of the students making them, just for the site. And obviously you have to discuss with your colleagues what you have done, what you have written in the poster.
Good morning, everyone. My name is Luca Di Cecilia, and I'm a PhD student at the University of Modena and Reggio Emilia. Today I'm going to describe the main topic of my doctorate research, which involves hyperspectral imaging of the human iris. Hyperspectral imaging is a technique that allows the acquisition of images with multiple spectral channels, usually more than 10, in contrast with state-of-the-art technologies in which the number of spectral bands is equal to 3, which corresponds to red, blue, and green channels. Hyperspectral imaging can be exploited to obtain a very fine spectral fingerprint of each pixel of the image. And this can be extremely important when we want to recognize the presence or either the absence of certain elements or components in the object that we are analyzing. So let's start with the reason for this study. A recent statistic from the National Eye Institute highlighted that the number of people affected by the 4 main eye pathologies in the world is going to double by 2050. Therefore, there's an increasing need for biomedical instrumentation that could diagnose and detect early these diseases. In particular, we focus our attention on AMD and glaucoma, as these two pathologies are both treatable if they are detected at a very early stage. We based our work on the hypothesis that there is a strict correlation between the development of certain ocular diseases and the iris color and structure. This was also demonstrated by previous published works that are reported in this slide. Therefore, in order to measure the iris spectral reflectance, we developed a hyperspectral imaging system. Moreover, to identify the iris structural features and patterns, we implemented and exploited some image processing algorithms and machine learning techniques. The experimental setup consists of a motorized monochromator that I designed and realized during my first year as a PhD student, a monochrome camera, and a PC that runs a custom Python software which controls the whole system. After each iris images acquisition, we obtain a hyperspectral data cube composed of 22 images at 22 different wavelengths. We then compute the reflectance pixel by pixel by using the equation reported in the slide. We also select the region of interest over which the reflectance is calculated. 8 volunteer irises were analyzed, and the average spectral reflectance, calculated as the mean of 6 acquisitions for each patient, is shown in the graph. Each patient's iris color was referred to a gold standard scale, known as the Franzen grading chart. Repeatability was evaluated, and it is extremely high among same patient and different sessions measurements. As you can see, for wavelengths lower than 700 nanometers, melanin absorption is the main dominant effect. In fact, darker irises who have a greater amount of melanin exhibit lower reflectances. On the other side, for wavelength greater than 700 nanometers, melanin scattering is the dominant effect. Therefore, lighter irises have lower reflectances in that range. To conclude, we demonstrated that hyperspectral imaging of the human iris is a promising technique. The instrument is currently used at the Fondazione Bietti per l'Oftalmologia in Rome, Italy, where it is used to acquire data on a large number of subjects. Further improvements involve the development of consistent techniques to evaluate the results, as well as the development of an optical model of the iris in order to better understand the light interaction with the ocular tissues. Thank you for your attention.
Hi everybody, I am Sonia Bergamaschi, the coordinator of the ICT doctorate course, and I want to introduce you to the poster session of the student of the cycle 32.
Good morning, I'm Marcella Cornia, my tutor is Professor Rita Cucchiara, and my research activity is about combining vision and language from saliency to captioning. In particular, I worked on visual saliency prediction on images, and then I work on image captioning improved by saliency maps. Finally, I concentrated on video captioning, and in particular I developed a video captioning architecture with naming capabilities.
Okay, may I start? Okay, so my name is Andrea Palazzi, my supervisor is Professor Rita Cucchiara, and I worked on road scene understanding through computer vision and deep learning throughout this time. And we first work on predicting the driver's focus of attention. So for this purpose we recorded a use dataset matching the human driver fixation with the outdoor scene and view of the road, and we trained a deep learning algorithm to automatically infer which are the most salient region in the image from the driver's point of view. And during this last period, I moved to the surrounding view of the scene, so trying to understand, for example, the bird's eye view of the road scene, or in this very last period, the 3D pose of the surrounding vehicles from the single monocular camera, so without additional depth or stereo information.
Hi, my name is Davide. I'm a PhD candidate here at the University of Modena and Reggio Emilia, and my research deals with, my advisor is Professor Rita Chiara, and my research deals with anomaly detection, which can be formalized as a binary classification problem in which you only get to observe normal data, one class, during your training, and most approaches are based on reconstruction, whereas we deal with density estimation. We want to estimate the densities of normal images, normal videos, and so on. So we employ autoregression, which is a technique to factorize the probability distribution using the chain law of probability, and basically you estimate the distribution of probability over the next variables by observing the previous ones. We introduce two architectures, and particularly two type of layers to perform autoregression over the feature space learned by an autoencoder, and this helps the autoencoder, this regularizes, imposes a regularization over the feature space in order to be to respect the autoregression constraints. So these are some results on NIST, CIFAR 10, and the drive dataset, in which we train only on one class and we test against the other ones. So we have nice results for all the settings, and this is some results, some qualitative results over an anomaly detection dataset in which the probability of the input clip is lower in the right points. For example, in this clip, a bicycle enters, and a bicycle is an object that he has never seen during training, so he is telling these anomalies in some kind of way, and the same for skater and pickups. So this is it, I guess.
Good morning, my name is Elena Cipressi, and I am doing a PhD apprenticeship at Empirics jointly with the University of Modena and Reggio Emilia. My research topic is the quality of experience in 5G networks, and since 5G is not standardized yet, I decided to start my research activity studying the quality of experience in multimedia video streaming. One of the most prominent challenges in the video streaming is the widespread adoption of encryption. For this reason, we decided to adopt a machine learning approach, interviewing people that will subjectively assess the quality of the video. So this research will be conducted in partnership with a Japanese network operator. Will give us the people to assess the video quality.
Good morning, my name is Giovanni Abruzzese. I'm a PhD student at the University of Modena and Reggio Emilia. My research interests include big data analytics, network science, and machine learning, all applied to cybersecurity, and my tutor is Professor Michele Colajanni. Here you can see a poster representing one of our most recent works, which focuses on the detection of pivoting activities in large networks. And pivoting activities, and in particular pivoting attacks, are a very important research problem in cybersecurity, because they are commonly used in a lot of recent cyber attacks. And in this work, we developed a novel algorithm to detect these attacks and prioritize them accordingly. The results show that our proposal is both efficient and is efficient at both detecting these attacks and ranking them accordingly, and is also capable of executing the analysis in a very fast way, which is appropriate for timely analysis.
Good morning, everyone. I am Federico Bolelli, a PhD candidate at AI Image Lab, and my tutor is Professor Costantino Grana. My research topic concerns optimization of binary image processing algorithm, and I focused the first year of my research on connected components labeling, developing a new model which is one of the fastest algorithms in the world. And beside this, I also worked on a project founded by a company and Emilia-Romagna region to automatically indexing historical manuscripts.
Good morning, I am Fabio Giovanardi, a PhD student from the University of Modena and Reggio Emilia.
My tutor is the Professor Luca Vincetti, and my research activity is focused on the DNA detection using inhibiting coupling fiber. This type of fiber helps us to infiltrate a particular solution, and we can see a shift of this spectrum proportionally with the thickness of a layer that is formed between a PNA probe and DNA. And we have done some experimental measurement using biotin and streptavidin, and in the literature is deep already investigated, and as soon as possible we done this measurement with the DNA.
Hi, I'm Davide. I'm a PhD student here at the University of Modena and Reggio Emilia. My field of research is automotive cybersecurity, and I'm under the supervisor of Professor Mirko Marchetti. In the first year of my PhD course, we focused on a part of the detection for automotive cybersecurity that results in the design and implementation of 3 different algorithms that were published in international conferences, where we inspected different parts of the vehicular network, in specific on the controller area network, the CAN bus, in order to detect the injection of malicious messages. And right now our focus is focuses on the triage and the reaction phase, where we already published one international conference paper on the reaction process.
Okay, I'm Luca Gagliardelli, and my tutor is Professor Sonia Bergamaschi, and my research topic is big data integration. In particular, I'm focused on the entity resolution problem, that is the task of identifying records that pertain to the same real-world object. And in particular, I implemented a novel meta-blocking algorithm to perform entity resolution on Apache Spark. Here we can see some results that shows that my new novel algorithm outperforms the state-of-the-art one.